We will get the complete presentation right sometime. So anyhow, you would be introduced, right? So okay, you'd be introduced and you would go up and present it. Once I need to make sure this is recording the voice. Otherwise, after half an hour, you find out that it's not recording, and then it is recording. Just that I don't know whether it is using the internal microphone or the external microphone. I don't know that bot. So hello, hello, hello. Anyhow, the first 1 minute you just discard it. Okay, good evening everybody. Today I'm going to present my research studies that I've been doing with Dr. Asapalli. The title of my presentation, the title of my research is Scientific Studies to Philosophy House and its congeners. I'm going to show you the Linoxidine, and I'm going to tell you about reporter synthesis, and I would speak about our plans as to how we make, and then give you the details of our progress and conclude. Okay, that's the outline of my talk, and I'll take the questions at the end if you have any questions. That's all I need to say on the slide. I don't want to say too many things because it's outline, right? So, and what is Linoxidine? Linoxidine is hexacyclic compound, as you can see here, 1, 2, 3, 4, 5, 6. And we'll get into the structural features of this molecule in a minute, but we'll look into the isolation things first. Linoxidine has been isolated from Liniaceae family. The Liniaceae family has been used in treatment of a lot of disorders such as rheumatoid arthritis, warts, and also they have been used in anti-cancer and antibacterial studies. So that's where our interest in this molecule is. And as you can see, that's the plant, Linoxidine, and probably this is isolated from the leaves. We need to find out where it is isolated from. Okay. So that's about the isolation. Renoxapine is not by itself, but it also coexists with other alkaloids. So these alkaloids also have been from the same plant. So the renoxapine is a new kind of alkaloid. So far, lignans, this system has not been precedented. There is no precedence for this oxypane ring. This is a 7-number ring, and that's a new lignin. These lignans are kind of known in different species, but this is the first report from Liniaceae family, and there have been some synthetic studies towards these alkaloids, but there have not been many studies for this alkaloid. I'm going to talk to you about some of those synthesis in a minute, but just to note, thymine C and retroheliozanthine and this dihydroheliozanthine, dihydrothymine C are congeners of linoxidine. Okay, that means they exist in the same plant. That has some relevance to us, which we'll get to in a minute. Okay, so why are we interested in linoxidine at all? We are interested for the structural aspects of synthetic chemistry as well, as synthetic chemists, but also we are interested for its medicinal potential because it belongs to a family of lignans and such as etoposide and protoxin. Etoposide and protoxin are known to be good cancer drugs. So if we can functionalize this at this position and at this position, we would have better prospects of finding new molecules for different types of uses. So we are into this molecule for two reasons. One is we can make this molecule as synthetic, we can develop new synthetic chemistry. At the same time, we can also have analogs to explore the biomedical potential. The biomedical potential has not been tapped fully. It remains to be tapped. It remains to be explored. So we are planning to do that. Okay. So what are the difficulties making the system, and how is it different from others? Others were not connected here. As I said, this is the first work system that is this kind of system. that is called the dihydroxygen system, dibenzodihydroxygen system, and there is a double bond which is highly strained, and there is a chiral center. So there are a lot of structural features that challenge synthetic chemistry. So there is a lot of interest in this molecule, and our group is involved. There are a few other groups from other parts of the country and other parts of the world. And so let me tell you about the first synthesis that was developed by PJ. I'm not going to go into the details, but I will just give you the flavor of what he has developed. They have developed this synthesis using the domino reaction catalyzed by palladium, right? So this is how they did. The first step is functionalization of this aldehyde. This aldehyde itself takes 4 or 5 steps to make. And once they have aldehyde, they functionalize using a Wittig reaction and then followed by some nucleophilic displacement to get to this kind of olefin. Once you have this olefin, the next step is to make this connection with bromo compound. This is also not commercially available, so they had to make this one synthetic precursors that takes about a couple of steps. And this is a Williamson ether synthesis, and they have connected this oxygen carbon bond that is going to be this bond in future in the latter stages. So they found this bond in the beginning itself. That's where we are going to differ, so I will rather highlight that bond formation that they have formed that bond in the first place. And then they do a domino reaction using this palladium source. First they do a Sonomachitta reaction. Sonomachitta reaction is a coupling between sp carbon and an sp carbon. It's an sp hybridized carbon and a sp2 hybridized carbon. So they do a palladium chemistry to attach the alkyne. Once they attach the alkyne, they try this domino reaction where they are forming one bond to this carbon and the next bond to this carbon using the same palladium species. That's why it's called domino reaction. More than one bond is formed in the same step, right? And so once they have this core in place, the last thing they need to do is close this ring. For that, the oxidation states have to be adjusted here. This alcohol needs to be oxidized. This carbon needs to be reduced and converted to alcohol. So this redox manipulation itself took them about 4 or 5 steps. Finally, alcohol. This is the key reaction. This is the oxidation state manipulation. So nevertheless, it's a beautiful synthesis, but it's a longer synthesis, right? And this next synthesis was developed by a group from Canada, Mark Lotens, published in the same year. This is one of the prestigious journals, so that it talks about the importance of this molecule. So again, he also uses palladium chemistry to make this compound. He combines 3 syntons, the one which is shown in red and blue and with 2 syntons. So they, all of them need to be made, except for this acrylate. This is called acrylic acid ester. Except for this, none of these are commercially available. They take about 3 steps for the first synton and 2-3 steps to get to this iodo compound. And once they have those 2 syntons, they make ether, Williamson ether synthesis, they make the bond again. The first bond is into this oxygen carbon bond. That's for the 7-member ring. So again, there is no flexibility here. They cannot make analogs here. They already have logged it up, right? So the next step is the next stage was to use a synthon which is made in 3-4 steps using this chemistry, and then this commercially available intermediate. And they do a Catalin reaction using palladium, and that makes more than one bond. Again, this reason is also called a domino reaction. Once you have this alpha beta unsaturated system, they ozonize this alkene to get to aldehyde, overall type of reaction, and then do an aldehyde condensation to close this bridge. This member ring is in place. They do another palladium reaction to close this ring, and that gives them an oxygen. Okay? That's fairly lengthy synthesis. So what's our plan? We propose to do we propose to execute a biomimetic synthesis. Why is it called a biomimetic synthesis? Because we propose to make this from dihydrothionein C, the dihydroxyxanthin, is also pointed to this molecule in the plant. So we thought it might be, there might be a way to convert this into this. That's how the nature is doing. So we thought of mimicking the nature. So we call this as biomimetic approach. So what is novel about our approach? We plan to form the thing at the end rather than at the beginning. True, there will be some difficulties in this approach, but we want to rather do this way because we can now do things like analogs. That's where the novelty is going to be. Because if you want to substitute these things, but we have to have the technology to find out its biological potential. Right? So for that, so the we plan to do this from that how we make itself. That can be made, or at least we propose to make this using an intramolecular deep-solder reaction. Intramolecular deep-solder reaction or a 4 plus 2 cycle addition. Right? So this is a diene system and this is a dienophile system, as you can see, and these electronics are matched. This is said to be a diene because it's electron rich. This is said to be a dienophile. This is electron poor because of the carbon atom. So we devise this system. Then on the paper, now we have to get into the lab and make. We have this synthesis. We go into the lab. We do this synthesis of the syntons, starting from this aldehyde, which is called pyphenol, and this is pretty inexpensive. 100 grams you can buy for about $100. Much more cheaper than that. So this pyphenol is commercially available. We do a Wittig reaction. This is again commercially available. This is a modification of Wittig reaction. It's called Wittig-Horner reaction. So the Wittig-Horner reaction gives this trans double bond in place. Whatever we have here, that is that. I'm going to show the elements in a minute. But this ester was further reduced with dibol to get to alcohol. That's one of the synthons that we need. Another synthon is done. This is the diene pot. The dienophile pot was made again from the same Wittig reaction. Instead, here instead of 1 equivalent of sodium hydride, we use 3 equivalents of sodium hydride and iodine in the reaction. So what happens is first it forms the olefin, this olefin, and then next it goes undergoes addition of iodine to make a diiodo compound, and the diiodo compound undergoes double elimination. So this goes to first this one and then from there to this one because we have iodine. So, but nevertheless, this can be done in the same pot. So this is the Wittig reaction followed by elimination of hydrogen halide. Two molecules of hydrogen halide is eliminated, and that's why we need extra base and iodine. So you get to the alkyl ester here, and this alkanoate or alkyne ester was subjected for hydrolysis to get to carboxylic acid. Now we have an alcohol and a carboxylic acid. So the next step is to combine them. How are we going to combine them? We could do it in different ways. We could activate the carboxylic acid chloride and all sorts of things. But instead of doing it in a milder way, this is called the Stiglitz esterification, where you use BCC to activate the carboxylic acid. This is the mechanism, as you can see. I'm going to put the mechanism here. So the BCC activates the carboxylic acid and the alcohol attacks the carbonyl, and this over leaves. BCC becomes urea, dicyclic urea, and then we have to move. So when we make this ester very clean reaction, we just have to filter the urea and titrate it and then take it to the Diels-Alder reaction. And we're going to come back to the Diels-Alder reaction, but let me show you the animals that we have for these symptoms. This is the ester now. As you can see, this is the CH2 for this methylene bridge, and this is the ethylene ethyl group, and we have an ethyl group here. Right? And if you want to see the alkene, trans alkene, how do we know that? Because of the coupling constant between these two. Right? So the distance between these two peaks, whether these two are matched. This would have a smaller coupling constant, trans would have a larger coupling constant. These two protons are alkene protons. One hydrogen here, one hydrogen here. Right? So the rest of the aromatic protons are here. So that's pretty convincing. And this is a little missing, little looks like little impure because this is how we got it from the reaction. We don't purify it, it's still reaction, we go forward and do the next step, the alcohol reduction. And as you can see, the ethyl group is gone now. There is no ethyl peak here. We get a new peak, that is for this CH2. So we know that we have alcohol. Again, this is impure. This is as it is octane. So let's pretty clean reaction. Then we couple it with this is the carboxylic acid that I told you. Acid peak. So the coupled product has this NMR. There is no acid peak further down the line. And there are two of these methylenes which are kind of two of these. So that tells us that there are two molecules combined and all the integration are one and all changes. So we have Diels-Alder. So it was time to do the Diels-Alder reaction. And as you can expect, the diene and dienophile can orient in two ways. This is one of the orientation where this double bond is acting as a diene. This double bond of the benzene ring is positioned for the diene. And in this case, the other ortho double bond. This is orthocarbon. This is the metacarbon, right? Compared to this oxygen. So the orthocarbon is chemically pure because it has to overlap with this carbon. Some compounds, so we can do this. So we purified these, and these are the NMRs for this. This is the mixture, as you can see in the mixture. As the Diels reaction was done, Diels reaction, and the rating of these compounds is calculated by looking at the compound. But you look at then however, these are the two significant this must be this methyl the major, you don't see that in the minor. The minor is, I'm going to show you the pure compounds in a moment. Major compound, where you see two patterns compared to the minor one, and the minor one. Oh, so let me go and show you the overlap of these two products. So as you can see, both of them have pattern here, but the only difference is that this have alpha proton. So having made these compounds in slightly higher ratios than what we wanted, lower ratios than what we wanted, we would rather want more of these because this is going to use the oxygen plus oxygen. But nevertheless, we have another antibiotics. We have those and those NMRs will be shown as we get ready. So having made these compounds, we ask whether we can take whatever the minor that we have and see if we can still make an oxygen, and then we revise the chemistry for making this. However, this didn't turn out to be as easy as we thought. We propose some mechanism and we do it here. And then we can let the suppose the decoder for aluminium ion. This aluminium ion is supposed to be after this amount of compound that we had into what we want is not very successful. So what can we do here? We need to make an amount, and moreover we should have it because so that we don't have to compete with this protecting rule. And so we went back to the drawing board and then revised the plan such that you don't have to deal with the deep protection. You already have a free hydroxy rule. We have already had that from the algorithm and the algorithm. So how do we get to this compound? Then we have to start with the first update. We have to do this one. Then we can do something. Or we can do two options here to see the ratios. So that's what we are doing. So where are we? We took a different aldehyde instead of pyranol, we use hydroxy, aldehyde. Then we did the liquid reaction the same way. So we have the then we do the technology, so the reaction, then we have the code, then we have the alcohol, we have alcohol, bomb protecting group is working with for the of machine and to close. Bomb protection, right? Used to protect this for bomb. The bomb protection group has continued, so we don't use the people that cycle the rack and more issue. However, that turned out to be not the case. So this is the NMR, as you can see, we have before. Nevertheless, so remind me. And then this alcohol, this is the regular protected alcohol. And the deal founders, as I said, didn't quite deliver the product. We expected this to be the orientation, but turns out that this type of growth is overweighing the pi interactions. So this is what we see mostly. If I go back to the drawing board and we purify that, so what can we do at this stage? We have to remove the bomb group and then try to build out the reaction again and hope that there is some sort of hydrogen bonding with the group. That's the logic behind trying to right now we're trying to do this. And moreover, normal for the ratio that we have here. So you can lay our hands on this one, then you can do local by doing local you can now see you can only have that's the advantage compared to other methods. Other people did their enough, but their method is has a drawback that you cannot substitute this problem. So each period you have to do it once, right? You have to do the whole thing because they have to go back to the drawing board every time and they have to start the synthesis again. But whereas here, you can say already different types of algorithm. Let's say you have 200 reactions. Can make 100 derivatives. That's the advantage of it. So what are the future plans? We also okay, don't say it doesn't work. So in future, we are also trying to see to the number of steps. By connecting this daily, but it's also kind of consistent. So this confirmation is wrong, the orientation that we want. So we don't have to that would be a short example for Rhinoceros. So this is what we already have. This one we made from Esther, right? You don't have to make it from right now. I mean, if need be, we can buy it. Fabric acid has a southern way around. So, two acid, use that. Okay? But anyway, we should buy fabric acid. So what do we need to change here to execute this approach? We just have a functionalizer of file. We already have the file. We need to put one method and one parameter on that. So we have to again go back and start with that on them. We do it as we speak. And we will follow this one. And as a result, we can find this takes 3 steps to get here. This is commercial arrangement. Acid 1 step. 3 steps we have So it's pretty straightforward, right? So that's what you want to execute quickly and see if you can. The other way around would be to see whether only one linker is enough. Instead of two linkers, that's something we are exploring. Let me conclude by saying that we have successfully prepared digital react because it's not scales. We executed 4 cycle addition reactions. As a result, we made some new natural products, dihydrothionein C and dihydrotetraxylianthin. And then we unsuccessfully explored oxidation chemistry, but we are confident that if we get the free hydroxy group, this chemistry will work. And in the process, we also make iron C and all these derivatives are being filtered from mathematics for exploration of the biological activities. Okay? And what is more important is quite our approach and the progress, which is shortly we are going to publish. With that, let me just give you a brief summary of what I presented. How will you compare with other approach? With that, I would like to thank our research group and this was just Gola for crystal structure. My name was the chair of the chemistry department, and all the other faculty of the chemistry department, and my friends and staff of the chemistry department. And I do thank you, Dr. Atman, for providing me opportunity to do your studies. With that, I would like to thank you for your time and attention. So it flows, right? I just wanted to give you some material so that you can have any questions, we can talk about it.